So the video today, this lesson is a fairly long one because it covers a lot of topics. They're important topics though, so we'll spend some time on these. So let's start by recalling what we saw in the last section. So we saw that we could approximate the instantaneous velocity by using the average velocities over short intervals. So the shorter the intervals, the better it was for us. So the instantaneous velocity at, say, time t equals 0, this was approximately, say, s of b minus s of a over b minus a, or we might have used d's before, but so what this is where the interval ab contains t, and let's say an s is the position function. So what we saw then was that the closer that these got together, the a and the b got together, the better our approximation. So this is going to lead us to the notion of a limit, which you saw already in the flipped class video. But let's just quickly recall that we write L to be the limit as, say, x goes towards some value x naught if, as x gets close to x naught, f of x gets close to L. So that was our notion of a limit, and we saw several examples of this in the flipped class video. So let's go ahead and consider some more examples here. So this example is going to be important later in the course when we talk about derivatives of sine and cosine, but for now it's just an interesting example on its own. So let's consider the function f of x, which is sine x over x. And this is, of course, only defined where x is not equal to 0, because if we tried to plug in 0, we would get a 0 in the denominator. We know we're not allowed to do that. But we can ask, so what is the limit if it exists? So not all limits exist, of course, as x goes towards 0. Of course, we can't just plug in 0. Sine of 0 is 0. Obviously, x at 0 is 0, so that would give me 0 over 0, which makes no sense at all. So what we can do, though, is we can start by looking at a table of values. So let's consider tables of values. So we're going to take some values that are close to 0 and see what's happening with this. So let's say I start with some negative values that are getting close to 0. And if you plug these in, the outputs we get are approximately these. Wait, there's one more 9 there. It's going to make a huge difference, but... And so this last value, when I plug it into the calculator, so this last value here, when we plug it into the calculator, it just gives out 1, or plug it into the computer. Sorry for the technical difficulties here with the program. So we can also look at values that are a little bit bigger than 0. So same values, just make them positive now. We can see we get the same things for these values. So from this, we might guess that the limit as x goes to 0 of sine x over x should actually be 1. So we could also draw a graph of this. So we could plug into the computer, a calculator, whatever you'd like to use, and just make sure that you pick values that don't contain 0. So if you were to do this, what this would look like is we'd have an open circle here at 1 because we're not plugging in x equals 0. And then the graph would go down like this value here being pi, and same thing over here, this value being negative pi. So just like before, we can see that if we were to take values of x, these different values of x, as they get closer to x equals 0, going in either direction, those dots there are approaching 1. So that tells me that my limit should be equal to 1. So that isn't a rigorous proof or anything that the limit is 1, just a good guess by using tables and graphs that that should be the value. We'll see later in the semester how to actually evaluate that limit precisely. It's not quite as easy as some of the other ones we'll see. So let's look at another example. So let's define our function in this case, and we're going to make this a piecewise defined function. So 2x plus 7, and then x plus 2 squared. And these values are going to be for x bigger than 1, and these for x less than 1. And we can ask, what's the limit as x goes to 1 of f of x, if it exists? So in this case, let's start out with our picture, and then we'll look at values afterwards. So I'm interested in here at 1. There'll be a few values here that are important. So we'll fill those in. And now if we graph this, this starts here, say it goes up as a parabola, and it stops there. It's not filled in at 1. We haven't defined it at 1. Then after that, it's just this line. So if we think about what this is, this part here is y is equal to 2x plus 7, because that's what our function is for bigger than 1. And this part here is the x plus 2 squared equals y. So from this we can see again, if we think about some values of x moving towards 1, we see our values here are climbing up towards 9 coming from the left, and same thing if we go coming from the right hand side, they're going towards 9. So from the picture it should look like that the limit as x goes to 1 of f of x is equal to 9. Getting the same thing coming from either side. We can also look at some values in a table to reinforce this. So if I look at x, so now if I'm coming from the left-hand side of 1, just to be clear what we're plugging this into, for the left-hand side of 1, that's the bottom one here, so we should be plugging in x plus 2 squared. So this is f of x, but let's go ahead and make that clear that that's what we're plugging into. So this is 8.41, 8.94, 8.99. And if we come from above 1, now we're looking at the function, the lines. This should be, we should be plugging into 2x plus 7. So if we look at 1.1, 1.01, 1.001, we get 9.2, 9.02, 9.002. So this table also shows that as we're getting closer to 1 from either direction, we're getting close to 9. Now, there's another way we can look at this. We could look at the limit as x comes from the left of f of x. And so in that case, this is the limit as x comes to 1 from the left. And now the function is x plus 2 squared for that. And you saw in the flipped class video that this is a nice function at x equals 1, so this limit we can just plug in the value. And then we can look at the limit coming from the right, which is the limit coming from the right. And now this is 2x plus 7. Again, this is a nice function, so we can just plug in the 1. And since the left and the right-hand limits are equal in this case, that means the limit itself is equal. So since the limit as x goes to 1 from the right of f of x is the same as the limit as x goes to the left of 1, and this is 9, we have the limit as x goes to 1 overall exists, and it's equal to that common limit. So this is something that was covered in the flip class video on how to do this. So if you recall, this limit coming from the left, so this is called, this one here, this is called the left-hand limit. And this one is called the right-hand limit. In this result we're using here in the bottom, let's just recall this. So we have, in just the end of the example, so we have in general, the limit is, say, x goes to a of f of x is equal to L if and only if the limit as x goes to a from the left of f of x is equal to L, and the limit as x goes to a from the right of f of x is equal to L. So both those limits have to exist and they have to be equal, and then that tells you the overall limit exists. So let's go ahead and try another example, kind of reinforcing this idea of left and right hand limits. So let's consider the function y equals f of x given by the graph Okay, so there's our axes. Now let's go ahead and put our graph down. So let's say we start here at 2 with a solid dot. We're going to go down, have an open dot here. Like this. So this is y equals f of x. Now let's go ahead and answer some questions about this graph. So let's evaluate the following limits. And just evaluate the following, because one of them won't be a limit. So for the first one, let's look at the limit as x goes to 1 from the left of f of x. Now for this one, what we should be doing is moving in this direction. So we see we're moving down along this. So this one's getting closer and closer. That dot isn't filled in there, so f of 1 is not equal to 1, but these values are getting closer and closer to 1. What about if we come from the other direction? Now if I come from the other direction, should be values going like this, so I should be going down like this. So we see this one's getting close to -1, and note that's actually what f of 1 is equal to as well. Now, if we ask what is the limit as x goes to 1, so as we see, limit of f of x, this does not exist because remember we needed the limits from the left and right to be equal for the limit to actually exist. Now what happens if we take the limit as x goes to 2 from the left? In this case we can see as we go up towards the x equals 2, we're going towards 0. And it's the same coming from the other direction. So overall, if I'm going towards just 2 overall, I get 0 as well. Finally, we might ask, what is the value of f at 2? Well, that's not equal to the limit in this case. It happens to be the value down here where it's filled in at. So this is actually equal to -1. Okay, so that's how we can read all of that information off from a graph. Let's consider another example, the word problem. It's really just taking some more limits, but with some variables here that make it a little bit trickier maybe. So let's consider the theory of relativity in physics. It says the mass of an object traveling at velocity v is given by, so this is one of the big results of this theory, is that the mass changes with the velocity. So you have to be going very, very fast to notice this, but it does make a difference. And so what are these terms here? Well, m0 is the mass at rest. So in other words, if v is equal to 0, that's what the mass should be, and you can just plug that in and see that that's what that should be. C is the speed of light, so this is a constant, and this is approximately, and I didn't write down what this is, it's approximately 300,000 or something like this. Sorry, this is approximately 299,792,458 meters per second. So it doesn't so much matter what it is, but it's a constant there. Okay, so let's go ahead and evaluate a couple of limits here. So let's start with the limit as v goes to 0 of m of v. So this is just the limit as v goes to 0 of m0 over 1 minus v over c squared to the 1/2. And now notice in this case, 0 isn't a problem in this function at all, so we can just actually plug that in. And so I should get m0 over 1 minus 0 over c squared to the 1/2. Well, 0 divided by c is 0, so this is just m0, which is exactly what we expected that it should be. Now, a little bit more tricky, so let's evaluate what happens as the velocity gets closer and closer to the speed of light. So it can't ever get above the speed of light, but we can let it approach the speed of light from below. Well, so this would be the limit as v goes to c from below of m0 over 1 minus v over c squared to the 1/2. Now this is a little trickier, so let's try to break this down and see what's happening with each piece. So as v goes to c from the left, notice the top isn't changing at all. So let's look at the bottom. So if I look at v over c squared, as v gets close to c, that gets close to 1. This gets close to 1, but it's always a little smaller than 1. Right, because v is always a little smaller than c, so v divided by c is always a little smaller than 1. So what does that mean? So 1 minus v over c squared, this goes towards 0. But since that second term is always a little bit smaller than 1, this is always positive. It's important to keep track of the sign here because we're going to determine whether this is going towards positive or negative infinity. And so overall that means then that if we look at what m0 over 1 minus v over c squared to the 1/2 does. This looks like it's going towards, we're going to put parentheses here because this isn't an actual number, but it looks like it's going towards 0, but it's going towards 0 from the right-hand side. So a fixed number divided by something going towards 0, this goes towards infinity. So you can see this just by plugging in some numbers. So think of, as you're going towards 0 from the right, if you were to look at, like, say, m0 over 1/10, this is 10 m0. m0 over 1 over 100 is 100 m0. So if we keep letting these things get smaller, say 1 million, this is 1 million m0. So that's going towards infinity. So as v goes to c from the left, m of v goes towards infinity. So our mass grows without bound as we get closer and closer to the speed of light. So one of the implications for this in physics is an object can never reach the speed of light because its mass would keep getting greater and greater as it got closer and closer to the speed of light. So it could never actually accelerate to the speed of light. So if we wanted to graph what was going on here, it would look something like this. So we know when v is equal to 0, we're up here m0, and then we know we can never actually reach the value when v is equal to c, so we'll draw a dotted line there, and that's at c. We can never actually get there, so it's going to come up, and it's going to go up towards infinity as it gets closer and closer to v is equal to c. So that's what our picture would look like for that. Let's consider another example with the same type of idea, but a little bit more familiar looking function. So let's consider, say, y equals f of x to be, let's say, x over x minus 2. So let's consider what happens as x gets close to 2. So we're going to have two things to look at. We're going to have going from the right and from the left. So if x goes to 2, well, let's look at the top first. Well, the top part just goes towards 2. Obviously, if x goes towards 2, x goes towards 2. So now let's consider what happens to the bottom as x goes to 2 from the left. So let's plug in some values into a table to get some intuition for this in case we don't see it right away. So let's say 1.9, 1.99, 1.999. This is negative 19, negative 199, negative 199. So we can see we're getting bigger and we're getting larger values in absolute value, but they're getting negative. So this might lead us to say that the limit as x goes to 2 from the left of f of x should be negative infinity. So how could we maybe have reasoned that out without creating a table? Well, again, the top part here is going towards 2, and the bottom part here is going towards 0. But bottom part shouldn't be an arrow, should be a subtraction. Now, since all of the values are less than 2, that bottom part is negative. So we can say it's going to 0, but towards the left. So overall, this thing is going to be negative, but it's getting larger in absolute value. So this is going towards negative infinity. Now let's try the same thing coming from the right-hand side. So maybe before we do the table, let's try to logic this out again. Well, the top part is going towards 2, and the bottom part, now all the values are x values are a little bit bigger than 2. So that means you've got something positive going towards 0. So it's going towards 0 from the right. again, if we're going to write this, we should put parentheses over this if we want to do this, because these aren't actual numbers. But that tells me it's going to be something going towards infinity. Let's kind of verify this with the table just to make sure our intuition matches up with some values. So this would be 21. This is 201. This is 2001. So that seems to bear out what we said above. So this is equal to infinity. So now if we wanted to graph what this looks like, kind of get an idea of what's going on here overall, so we have here, if I go out here to 2, the function's not defined at 2, so I can put that there and put an asymptote. And as I come from this side, I go towards infinity, and as I come towards the other side, I go towards negative infinity. And we also can see if we plug in 0, we get 0. And now what's going on from the rest of it isn't clear from what we've done so far, but if we graph it, say on the computer, it looks something like this. And what we can see is these values here are actually getting closer and closer to 1. So we could ask ourselves then, this is our y equals f of x. So the natural question here is, what's happening as x goes to infinity and x goes to minus infinity? Because it looks like it's going towards 1 in either direction from our graph. So before we ask that, maybe we want to remember here that this thing here is called a vertical asymptote. So these generally occur, it's not only when there's a 0 in the denominator, because for instance the natural log has a vertical asymptote at x equals 0, but often they're going to occur when there's zeros in the denominator. Okay, so as it goes to infinity or negative infinity, so we say the limit as x goes to infinity of f of x is equal to L if as x gets very large, f of x gets close to L. Okay, and similarly to for negative infinity. And in that case, we refer to y equals L as a horizontal asymptote. Okay, so one really important one that's going to come up a lot, so important example that you'll want to remember is that the limit, say as x goes to infinity, of x to the n, this is going to be infinity if n is bigger than 0, and it's going to be 0 if n is less than 0. So think of the difference between like what's happening to limit as x goes to infinity of x squared. This should be infinity, but the limit as x goes to infinity of x to the negative 2, this is the limit as x goes to infinity of 1 over x squared, and this is going to be 0. So those ones are super important to remember. So let's look back at our previous example then that we were just doing, and we saw that that one went to 1. So let's see how we can actually show that. So the limit as x goes to infinity of x over x minus 2. Now for some of you, you might have seen this if you took calculus in high school, where you just said, oh, it's the coefficient of the biggest values of x. We're not going to allow that in here. I want you to actually be able to see why this is true. So what we can do is we can just multiply this by 1 over x by 1 over x, and notice that this is just, I'm just multiplying this by 1, so I haven't changed anything. And so now if I FOIL that through the top and the bottom, I got the 1 over x because that was the highest power of x in the numerator and the denominator. If I multiply that through the top, I get 1. If I FOIL it through the bottom, I get 1 minus 2 over x. And we just saw above, as x goes to infinity, 1 over x goes to 0, which means 2 over x goes to 0. So this is just 1 minus 0, which is 1. So that tells me y equals 1 is a horizontal asymptote. And now it's always, when you're asked for horizontal asymptotes, it's always important to check as it goes to negative infinity too. In this case, it's not going to make a difference for us, but in some cases, they might not be the same. So we're just going to play the exact same trick we just did, divide the top and bottom by x. So again, we'll get this term. And now as x goes to negative infinity, you're dividing by 2 over something that's very large in absolute value, so that still goes towards 0, which is 1. So if we go back to our picture from before, we can see that that horizontal asymptote, that's exactly what it's telling us here. It's saying, as my x gets really big, say what's happening here, well, it's going off towards infinity or going off towards negative infinity in either way. Okay, so let's look at another example from physics. Let's look at the force between two objects due to gravity. So each object gets the same force on it, and so this is given by F of r is equal to g m1 m2 over r squared, where g is the gravitational constant. For us, all that it matters is that it is constant. m1 is the mass of object 1. m2 is the mass of object 2, and r is the distance between the objects. And so we can ask here for a couple of limits of what's going on. So let's look at the limit, say as r goes to infinity first. So let's let these things get further and further apart and see what happens to the force of gravity between them. So if I look at this one, this is the limit as r goes to infinity of g m1 m2 over r squared. And now g, m1, and m2 are constant, so I could actually bring those outside of the limit if I like. And we just saw above, we'd set it with x's, but the variable doesn't matter. That thing's going to go towards 0. So this is g, m1, m2 times 0, which is just 0. So as we let the objects get infinitely far apart, the force due to gravity between them goes towards 0. Now, what would happen if we let them get really close together? So we'll let the distance between them go towards 0. Well, now this is the limit as r goes to 0 of g m1 m2 over r squared. Again, we can factor that constant out front. Well, now as r goes towards 0, we saw above that this is going to go towards infinity. So this is infinity. So as we let them get arbitrarily close together, this is going to get closer and closer towards infinity. It's going to get very, very large. Okay, so let's consider another type of example now for real-world implications. So you might have seen before, usually when we model population growth, it's often given by exponential functions. Where here P0 is our initial population, and K is some kind of growth rate for our population. But this isn't particularly a very good model to use long term, because exponential growth, as we know, is very fast, and very quickly we're going to run out of resources and room for our population. So this doesn't work long term. So there's another model that works better for this. So for this model, we'll write P of t is equal to L P0 over P0 plus L minus, sorry, I messed that equation up. So let's say L P0 over P0 plus L minus P0 e to the minus kt. And so most of these things look familiar. We know P0 is still the initial population. The K is some kind of growth rate. What we'd like to say is, well, what does this L mean? So P0 is equal to the initial population, or at least we think it should be. Maybe we should check that. Put a question mark there. And then we can ask, what is L? And of course, then we'll graph this to see what's really going on and why this is a better model for populations. This is a better model for population long term. So when a population first starts growing, the exponential works well, but over long term, it doesn't work so well. So let's see what would happen to this at t equals 0. So that would be our initial population. Well, what's happening there? I have L of P0 over P0 plus L minus P0 e to the 0. E to the 0 is 1, so this is L P0 over P0 plus L minus P0. Notice those P0s in the bottom cancel, so this just gives me L P0 over L, which is P0. So this is actually the initial population. So that's good. So we still make sense that we're using P0 for that constant. If it wasn't the initial population, we should have chose a different thing to denote that. But now let's see what's happening to L. What is L? So let's see. We said this is a better model of the population long term. So what does long term actually mean? So this is important because often you might be asked what happens to this long term, and you'd like to know, well, what does that even mean? So when someone says that, this usually means let t go towards infinity. So let the population keep growing. So let's look at what's going on with this then as t goes towards infinity of p of t. Well, this is the limit as t goes to infinity of L P0 over P0 plus L minus P0 e to the minus kt. Now, let's look at what's happening here. If we look at it, this is the only term with a t in it. Everything else is constant. So what we'd really like to know is what happens to that as t goes towards infinity. So we really need to know So maybe we can remember from the review video on exponentials, if we graph an exponential, so since we always want k to be bigger than 0 for our growth here, so what's really going to matter is what's happening to this function. So we know at t equals 0, we should be here at 1, and it should go something like this. So as t goes towards infinity, e to the minus kt goes towards 0. So limit t goes to infinity of e to the minus kt is equal to 0. So if we look back up at our equation there, this part that I have circled in blue for our limit up here, this part here, this is going to go towards 0. So the limit as t goes to infinity of p of t should be equal to, well, I have an L p0 over p0 plus, and then I have L minus p0, but then that part there is going towards 0. So this is just L p0 over p0, which is L. So what that L is the limit that our population approaches as t goes to infinity, is the stable population as t goes towards infinity. So if we were to graph this, so this is called the logistic model. I didn't say this above, yeah. So this model, so if you take any biology, you're likely to see the logistic model show up. So let's graph what that looks like. So we know that we're going to approach this value up here of L, and we know we start down here, say at P0, and there's going to be an important point we'll see later, so take this to be L over 2. We'll look at this later in the course to see what's actually going on here. I want this to be blue, so this should go up, and then kind of switch over and go like this. So this is y is equal to p of t in this case for the logistic model. So you can see this first part here, this does looks exponential. Right, because it starts off and then it starts curving up very quickly there. I could draw it a little steeper, it'd be more accurate. And then it slows down. So you want to think of this kind of when the population hits L over 2, what's happening here is now the resources and the amount of space are starting to take a toll here, and the environment can't support a population growing so quickly. So the growth starts to slow down, and then it basically levels off once you get really close to L. So this, we say this grows quickly until p of t equals L over 2. So we'll see how to figure out that L over 2 later in the course. Then the growth slows until it levels off near p of t equals L. Or let's say near y equals L, because p of t will never actually be L. So as I said, this shows up often in biology. So if you study biology, you'll see this quite a bit. So it's nice to kind of have an idea of what's going on here before you see it in biology. It shows up in other areas as well. So the logistic equation so basically anytime you have something where its growth is limited by kind of the environment that it's in, so that it can't just grow quickly forever, the logistic equation shows up in those types of models. So a couple of examples this might show up with is the spread of a computer virus. right? It can spread very quickly at first, but eventually it has to start leveling off because it runs out of places to spread. And another thing it's been used for is to predict when oil production will peak. So you're thinking about, okay, how much oil can the U.S. produce? Well, this can kind of give you an idea of at some point the production is going to essentially level off and it won't be able to continue to grow with how much we're able to produce. So another important concept that was discussed in the pre-class videos is the notion of continuity. So we saw there that the intuitive notion is a function's continuous, which I'll often abbreviate as just CTS, if you can draw it without picking up your pencil or pen or whatever you're drawing with. So that's a nice intuitive notion, the one you'll probably actually think about most of the time. But the more precise way to say it is we say y equals f of x is continuous at a point x equals a if the limit as x goes to a of f of x is actually equal to f of a. So that means the function has to actually be defined at a as well, and it has to approach it from the left and the right. And overall, it's continuous if it's continuous at every point. Well, let's just leave that part off. So it's continuous if it's continuous at every point. A lot of times we're going to ask for where functions aren't continuous because they're going to be continuous at most places. So let's go ahead and see an example of this. So let's draw our graph here. So let's say here at 1, we're going to put a circle here and a dot here. We're going to have, this will be here at 2. Put 3 here and 4 here. And so let's say our graph goes up like this, gets to there. It's going to go up like this. So 2 is a vertical asymptote for us. So I'm going to come down, open dot here. A little bit below that, we'll put a closed dot over here like this. I don't know why that all of a sudden just erased. There we go. Evidently it doesn't like me drawing this. There we go. Okay, so where is, so this is the function y equals f of x. Where is y equals f of x not continuous? So think about if you were drawing this, where would you have to pick up your pencil? Well, as you go towards 1 from the left, you hit this open circle. You've got to stop, go in and fill in this dot up here, and then go back down. So x equals 1 is a problem. Now as we continue along, we get towards 2, and now we have a vertical asymptote, so we have to stop, come to the other side of the vertical asymptote, and keep going. So notice, even though f is defined at 1, it's not continuous there. And so you could see, if this was, say, at 1, we could say the limit as x goes to 1 of f of x is 1, and then maybe say this is at 2, but f of 1 is equal to 2, so they're not equal if we want to think about it in terms of the limit definition. Now continuing past 2, as we go down along the curve, we get to this open circle at x equals 3. Have to pick the pencil up and go down towards 1 here and continue, so it's not continuous at 3. And then as we go across to 4, there's an open circle, so I have to stop, pick my pencil up over the open circle, and then start again. So it's not continuous at 1, 2, 3, and 4. Okay, so let's end this with a couple more examples of types that we're going to be seeing as we continue into the next section. So let's just evaluate a couple more limits here. And these are going to be important limits going forward. So let's look at the limit as h goes to 0 of 2 plus h squared minus 4 over h. So we're going to eventually see that this is a slope. This is without the limit there, that is the slope of some secant lines. And you take the limit, we'll see that this is going to give us a tangent line. But for now, we can just do this with algebra without worrying about what it means. So if we FOIL out the first term, I'm going to get a 4 plus 4 times h plus h squared. So that's just FOILing that out, right? Because I have 2 plus h squared is 2 plus h, 2 plus h. And so I FOIL this out for our practice. So I get 2 times 2 plus 2 times h plus h times 2 plus h times h. And that's 4. And then I get 2 copies of the h there, so 4h plus h squared. So that's where that's coming from. Now notice that the 4's in the top cancel out, so this becomes the limit as h goes to 0, and then I get a 4h plus h squared over h. And now I still can't plug, so if you look at the beginning, we couldn't just plug in h equals 0, because in the top I'd get 4 minus 4, which is 0, and on the bottom I would get 0. But here we still have the case, if I plug in 0, I get 0 on the top and 0 on the bottom. But what we can do to help that is I can factor an h out of the top, because there's an h in both terms. And now I can cancel that h from the top and the bottom, and I end up with just 4 plus h. And now I can just plug in h equals 0, and this just gives me 4. Let's do one more example. In this case, we'll see kind of a trick to help us with these types of limits that shows up quite often. So let's look at 9 plus h to the 1/2 minus 3 over h. So again, if we were to just plug in h equals 0, on the top I would get 9 plus 0 to the 1/2, which is 3. So minus 3, which is 0. On the bottom I get 0. 0 over 0 doesn't make any sense, so we can't just immediately just plug in for what the limit is. So what we're going to do is we're going to do a trick. So I'm going to multiply this thing by 1, but I'm going to multiply it by 1 in a funny way. So I'm going to consider 1 written like this. So the idea is this works a lot when you have, on the top here we have 9 plus h to the 1/2 minus 3. This will turn a lot. So instead of multiplying it by 9 plus h to the 1/2 minus 3, change that minus 3 to a plus 3. And now we'll see we're going to get some nice cancellation here. So you'll see some more of these in the homework as well, so you get used to this. So if I FOIL this out, I'm going to get a 9 plus h to the 1/2 times 9 plus h to the 1/2 plus 3 times 9 plus h to the 1/2 minus 3 times 9 plus h to the 1/2, and then minus 3 times 3, so minus 9. And on the bottom, we're just going to leave things alone. Okay, so the first thing we can see right away is that this term and this term, those are going to cancel out because there's a plus and a minus 3 there. And then I have a 9 plus h to the 1/2 times 9 plus h to the 1/2. So that just becomes 9 plus h. Those 1/2s go away. So I just get 9 plus h. And then I have this minus 9 at the end, and this is all over h times 9 plus h to the 1/2 plus 3. Now, the 9s will cancel in the top because I have a 9 minus a 9. So I'll just get h in the top. I have the h in the bottom, and then I have 9 plus h to the 1/2 plus 3. Since I have an h in the top and an h in the bottom, those will cancel out. And I'm going to get the limit as h goes to 0, and I'm going to have 1 over 9 plus h to the 1/2 plus 3. And now the nice thing here is if I just plug in h equals 0, I get 9 plus 0 to the 1/2, which is 3, plus 3. So this just becomes 1 over 3 plus 3, which is fine. This is just 1/6. And that's our answer. So you'll see this trick of kind of multiplying by, we call this the conjugate here, where you just change the sign of one of those terms. That shows up fairly often. It's quite a useful trick to have.